Welcome to the class. We were discussing Wittig reagent. I have just given a question. What is the reaction between water and Wittig reagent? Wittig reagent, this carbon is having negative charge, so it picks up this proton in water. Oxygen will pick up phosphorus will pick up oxygen, carbon will pick up hydrogen. So it becomes triphenyl phosphine oxide and a methane gas. Now you can easily understand in this reaction why we are using two equivalent. This is a stabilized Wittig, and in this case we are using two equivalents. Now you can easily understand why we are using two equivalents here. Any guess? You can easily write the product. It is a stabilized Wittig, so it will give us E double bond. Now anyone can give the reason why we are using two equivalents? This is a Wittig-Horner reagent. It is an example for stabilized Wittig. Okay, though we are having alkyl group, but phosphorus is having oxygen. This is a phosphine oxide, so it is a stable. It is an example for stabilized Wittig. In this reaction, n-butyl lithium will pick up a proton from this carbon. Then it will undergo coupling with this carbonyl. We are converting that oxygen into an ester. Then we are reducing that. We have alpha ester and sulfonate groups. When we treat them with sodium amalgam, that will result in a coupling. So the product here is E double bond. In this case we don't get any Z double bond. Okay, so this is what is called Julia olefination. Julio olefination. Here we don't get any cis double bond. We do get trans double bond only. So what we will do, we will take a sulfonate. When we treat it with a base, an anion will be generated that will be condensed with a carbonyl. So we are getting alcohol here. Alcohol will be converted to ester using this acid chloride. Then we are just a minute. So we are converting that into alkene by reducing with sodium amalgam. This is called Julia olefination. This is Julia olefination. Now, I have asked you a question why we are using two equivalents in this case. Why? Because we have an alcohol group here. So Wittig reagent. One Wittig reagent will pick up a proton from this. So that is why one Wittig reagent will be used, will be wasted here, right? So that is why we must use two equivalents. We'll write more number of examples. So this is an Arbuzov reaction. Then we will treat this with a strong base. In this case, we are using dimsil anion of dimethyl sulfoxide. So then we generate a Wittig reagent here that will undergo intramolecular Wittig reaction to generate the cyclic compound. So what is the product? 1, 2, 3, 4, 5. So we will get a 5-member ring with double bond. Take the notes. Another variation in the Wittig reaction is Wittig reagent which is having an ether, This is a stabilized Wittig because YME is a good electron donating group. Write the product because we are having an enol ether. We can hydrolyze this in the next step. We can hydrolyze this. So when we hydrolyze this, we will get aldehyde. So this is the product. Another important variation in Wittig reaction is when we use stabilized Wittig, what we will get? We will get this is a unstabilized Wittig. So when we use unstabilized Wittig, the product is Z double bond, right? Z alkene. But it is also possible to get E double bond. How we get E double bond with unstabilized Wittig? We need to isomerize this. With the unstabilized Wittig, we will get this syn oxaphosphatane. If we can isomerize this to anti-oxaphosphatane, then it is possible to get trans double bond. So to isomerize this, we will treat this with a strong base, either phenyl lithium or N-butyl lithium. When we treat this with oxaphosphatane with syn oxaphosphatane with alkyl lithium, then it will open up. Okay. Generally, it picks up a proton from this carbon. 1, 2, 3. Fourth carbon was there. Fourth bond was there. So alkyl lithium will pick up this proton, so it generates anion here. Because of this, the oxaphosphatane ring will be opened. When we generate anion here, this will be bonded to lithium, right? Because we are generating anion which may assume sometimes planar configuration also. In that case, these two are having spherical crowding when they are seen to each other. So that is why to get stabilized, what will happen under this condition, the anion will undergo isomerization, so that now it becomes anti. Now it becomes anti. Then we will treat this with tertiary butanol, so that anion will be quenched, and the Wittig will generate E double bond. So from unstabilized Wittig, if you want E alkene, what we need to do? We need to add alkyl lithium reagent. We need to add alkyl lithium reagent. Then we can get E alkene from an unstabilized Wittig. This reaction is called as Schosler-Wittig reaction. This reaction is called as Schosler-Wittig reaction. Wittig can also be used to open the epoxides. Generally, alkyl lithium salt of Wittig, so that means a simple Wittig CH2, when it is treated with alkyl lithium, one of the proton will be removed by alkyl lithium. Okay, this compound is this Wittig reagent is generally used to open the epoxides. Of course, we know the ring opening of epoxides is always anti hydrogen triphenyl phosphine. Now the Wittig reagent is still active, right? Wittig reagent is still active. That means we can convert, we can treat this Wittig with one more carbonyl. What is this Wittig? It is a unstabilized Wittig, but still we have alkyl lithium in the reaction mixture. So that is why we will get E double bond. It is a stabilized Wittig because it is simple R group, but still alkyl lithium is there. Because of the alkyl lithium, the syn oxaphosphetane will be isomerized to anti-oxaphosphetane. So that is why we are getting E double bond here. We are getting E double bond here. So in the same reaction in situ, we are opening the epoxide with a Wittig, then we are having Wittig reaction with one more carbonyl. Now we will discuss Horner-Wadsworth Emmons reaction. What is this? In short, it is generally called as HWE. HWE is a stabilized Wittig reaction. When we say a stabilized Wittig, it gives E as the major product. Okay. What is the Wittig reagent we use in Horner-Wadsworth-Emmons reaction? In Horner-Wadsworth-Emmons reactions, we generally use phosphine oxides, and we also use alkoxy. Generally, we have used triphenyl phosphine, something like that. Okay, but in this case, what we are using? We are using phosphine oxide with alkoxy substituents. Alkoxy alkoxy substituents. Because of these things, it is a stabilized Wittig reagent. So when we use this, it is a more nucleophilic in nature. At the same time, it is a stabilized Wittig. This is acetonitrile, a solvent. Wittig reagent will only react with carbonyl, either aldehyde or ketone. So when we treat this phosphate, okay, this is a phosphate reagent. When we use phosphate in the Wittig reagent, they are more stabilized. It is called Horner-Wadsworth-Emmons reagent. When we treat HWE reagent with a carbonyl, what we will get? We will get E double bond. Here negative charge is not there, that is why we are using a base. Another, see, what is this? A carbonyl was there, it was protected with 1 comma 2 ethane diol, right? A carbonyl was there, it was protected like this. After the Wittig reagent, we can hydrolyze. Acid hydrolysis will again give this, right? What is the importance of HVZ reaction? HWE reaction. When we do a Wittig, the byproduct here is phosphate. This is called phosphonate. The beauty of this is that phosphonate is water soluble. Phosphine oxide, it is not water soluble. So when we do Wittig reagent with triphenyl phosphine or trialkyl phosphine, we need to remove that from the product in a column chromatography. But in this case, because this phosphonate is water soluble, this will be separated during the workup itself. So that means we don't need to separate this compound during the column. It will not be there. Okay. So HWE are better compared to normal Wittig reaction. Okay. So the major advantage is that the phosphonate byproduct is water soluble. So this will be purified at the workup stage itself. We don't need to purify this during the column. This is called bis trifluoroethyl phosphate. I am not writing the complete name. It is bis trifluoroethyl phosphate. I am writing this part only. It is called still Janari phosphonate. This is called still Janari phosphonate. And similarly, we also have diphenopsy. This is bis phenyl phosphonate. and we also have Sai Switcheva. We also have one more reagent, కింద switch. This is called bis 2,6 difluorophenyl phosphonate. All these reagents, they are they look like they are stabilized, but all these reagents will give us Z double bond. All these phosphonate nates, all these phosphonates will give us Z alkene. All these phosphonates will give us Z alkenes. Okay, I'm not discussing the examples for these things. All these reagents will give us Z double bonds. Okay, right. I'll give two more examples.